Hi, my name is Monia Hussein, and this is my lab 4 on oscillation. So this is an overview of what I'm going to do. I'm going to talk about the introduction, Newton's second law and formulas, experiment, video and tracker, computations, glow script, graphs and errors, and what if questions. Introduction/purpose. In this experiment, I will analyze the motion of a spring mass system where the mass is oscillating in an arc. It will be shown how the system follows the energy principle by comparing it with computational models from my glow script code. I will go over the system and surroundings in the next slide. Two main fundamental principles we should focus on is Newton's second law, the momentum principle, and then the energy principle. And here we have another way of writing F net, F spring plus F grab, and this is the expanded version to get variables later in computation. This is the energy principle, where the change in energy in the system is the amount of work done by surroundings plus heat. The system is the mass, spring, and earth, and there are no surroundings, which means change in energy should be 0 since there are no work done and no heat. And these are the energy formulas written out, and this is the period equation to find the spring constant. Experiment setup, I will be using tracker to track the oscillatory path of the mass in the video sample using the data collected by tracker like the time of oscillation and initial conditions. I will determine the spring constant and relaxed length of the spring. Then using those data, I will create a computational model of the oscillation movement. Then I will compare the computational model with our tracker model. So here is my video. So this is my tracker data, the initial position, initial velocity should be starting from rest. These are the given data. This is my period calculation. I basically took the differences between the top data. I took 3 of them and then averaged them to get the average time. And here I used that to find the spring constant and the relaxed length. So here's my glow script code. So this is the initial conditions that I found. This was a given mass, and this was my position, initial position, and initial velocity. And these are the constant and relaxed spring that we found in the last computation or slide. Here is the spring length and spring direction equations. Here are the kinetic gravitation and spring potential energy formulas and added them together. Through the while loop, we have the ending time from tracker, and here we have gravitational and spring force and net force equations, and the velocity and position update formulas, and these are the same equations as stated before to find the change in energy in each time step. Observations and errors in a realistic setting. The system is not isolated from the surroundings, so there will be work done from the surroundings. For my mistakes, this is probably due to a coding error I was unable to resolve, or my tracker data was off. I probably did not accurately place the center mass on each frame. I was able to fix my y graph to be more accurate by adding the x and y's L naught before I had y's at L naught. And because of that, the model would be way higher than my experimental data, and it was becoming off. But now it's a little bit closer to a more accurate graph. So this is the what if questions. Is the energy principle satisfied? I would say yes, because we have no work done on the system because delta E is 0 and no heat on the system. But delta U spring is a bit off, and that could be from my last reasonings as to my errors from tracker or the code that I'm unable to see. So what if I didn't use the y graph data and use the x graph data using the same procedures? I would get the average t, and then using that t, I put in the k constant formula to get this, and then the relaxed length formula. And as you can see, that picking different directions will give us different values. And so we could probably get a different graph or spring constant, spring length and it will affect the computational model. Thanks for watching.